Hey, everybody. We'll wait another minute or two just to see if we can get a quorum. Uh, we don't have a huge lecture today. Going to be doing a little bit more on smart pointers. And today we'll wrap up our lecture on smart pointers. So I'll put it back on mute and I'll just check back in with you in a minute or two. Okay, well, I think maybe we'll get started. Maybe just if a couple of you would show me some hands, just make sure that you can hear me out there. Cool, great, thank you, appreciate that, awesome. Yeah, it would be tragic to lecture with my mic off. Okay, so we're going to talk about, we'll kind of circle back, review our smart pointer and unique pointer stuff from last week on Thursday. We'll expand that into talking about weak pointers and some specific application for weak pointers, and that'll kind of wrap up our smart pointer discussion for this semester. So hopefully you'll be able to apply this stuff when you get to your homework 8, which is the follow-on exercise to homework 7. So the stuff that we're kind of wrapping up today should give you everything you need for the homework 8, but you don't need to really worry about that until next week. And it's a pretty easy assignment, as we'll see once we get there. But I'll kind of point it out as this stuff comes up during the lectures, just to kind of help anchor it in your memories. Okay, so just looking at the rest of the semester, we're at week 13. We got about 1, 2, 3, 4 weeks of lecture left, and I'm kind of looking at how to shift stuff around. I've expanded stuff a little bit given our online format, just to try to make sure I didn't lose anybody. So we may lose 1 or 2 topics, but I'm going to try to stick to what you see here on this schedule. But I'll let you know. Definitely the homeworks and the quizzes will stand. Those dates won't change. We just may have more or less a little more review at the end rather than some new topics, which will take a little bit of pressure maybe off of the final exam. So, but I'll try to keep you updated on that at least once a week in case anything changes, so you know. And I'm a little bit behind on updating the homepage with the syllabus on it. I'll try to get the nuts and bolts of this up there, but all of these things I think are published in the calendar, so they shouldn't be any surprise to you at this point. Okay, so let's talk about what we're going to go over today, some quick announcements, and then we'll review the unique and shared pointer stuff, high level we talked about. I'll do a little quick hint on homework 7 just to help get everybody over the hump. I really want to make sure everybody does okay on this one. And then we'll do a little bit of more practice on shared pointers because I realized I hit you with a lot of stuff last week on Thursday. And then we'll dive into weak pointers and do some practices on that. The weak pointers are a little more esoteric. We'll spend a little bit of time on them, but you won't get tested heavily on them. The stuff you'll use most in real life, I think, will be shared pointers, but we'll try to go over some of the key benefits of weak pointers in case that comes up down the road when you're working in C++. Okay. Okay, so that's what we're going to cover today. And then just a reminder, so you have Jigsaw due on Monday night. Don't hesitate to send me email, questions, etc. Just in case you get stuck on anything. But we'll go over a little hint on that today to help you out. Quiz 5 should be posted now. So quiz 5 has 14 questions, about 7 points each. I think I put 2 in there to round everything off at an even 100, just to make it easier to kind of estimate your grading. But that's going to cover all the way through today's lecture, predominantly the dynamic, traditional pointers, new and delete, all that stuff we talked about, and then the smart pointers all the way through what we covered today. So again, if you want to click into the Quizlet link there, you can, or at the end of the lecture here, I'll have all of the links that are relevant to this smart pointer topic, but you need to combine those with all the other links that I put up there too. So, but all of that is in the Quizlet link. If you go to this link here, you'll see that stuff. Okay. Any questions on timing, schedule, topics coming up? Okay, and just to reiterate, there will only be 9 homeworks, not 10. So I just didn't think there's enough time to cram in the 10th homework. So I'll just give you plenty of heads up on that as we kind of wrap stuff up. Okay. Okay, so smart pointers, just a quick review of smart pointers from the memory library. So these things are a collection. There's 3 different kinds of pointers. They're generally referred to as smart pointers, but they have specific type. They come from the memory library. The unique we talked about, which only allows a 1-to-1 correspondence between this instance of the unique pointer class and the item on the heap that it's managing. And that's by definition, and part of the way that's managed is by deleting the a copy and assignment operations. Shared pointers, we played around with a little bit. They allow us to do more typical things like you're going to be doing in homework 7 with raw traditional pointers. That is, you have something on the heap and it can be pointed to by more than one thing. Shared pointers allow us to clean that stuff up very elegantly. In homework 7, you're going to have to do a little bit of heavy lifting in your destructor for your puzzle class. But once you convert this over to shared pointers, in homework number 8, you won't have to write any of that code because it's all done for you. So we'll do it the hard way first in homework 7, and then homework 8, if you choose to do this conversion via homework 8, that's one of the homework 8 options, and you'll actually see how much easier that is. So we're going to try to spend a little more time today practicing this stuff so that homework 8 will be a breeze when you get there, if you decide to take that path. And then weak pointers, of course, this is just so we can keep an eye on how many shared pointers are out there for a particular piece of memory without contributing to the count. We don't want to have a weak pointer affect the count or usage of the references to a specific piece of memory, because we just want to know how many people are using, say, an integer on the heap or an instance of foo on the heap. So the weak pointer allows us to do that. Okay. So here's the links to all this stuff, including the weak pointer, true false stuff. There's no code samples there just yet, but I think the key stuff that I'm hoping you'll internalize or memorize is going to be in the weak pointer, true false stuff you see there. Quick review on the code syntax. So you may recall this is our class name, or the type. This is the template type. So we're going to be pointing to integers. And then this is the name of the instance of unique pointer that we're creating. Okay. So that instance name is the name of something that's sitting on the stack generally, right? So this is on the stack, but it's going to be managing something on the heap. And remember that the constructor for unique pointer instantiation for unique pointers and for shared pointers requires a pointer to something on the heap. And that's what this new int gives us, right? So that's how we actually set up a unique pointer. And it's really the same for a shared pointer as well. And the really key thing to remember is that the new thing that we're creating on the heap has to match the template type. I'm sure I probably said that way too many times already, but so here's a little more code just to kind of drive it home. So there's our unique pointer uNull. I just called it that because it is null when it starts out live, but we of course can assign it to something else down the line. We can test it with a simple Boolean condition. This is overloaded. So uNull is the name of an instance of this class, right? It's not a pointer, but I can say if not uNull because the not has been overloaded in this class. So we've seen a lot of that, right? Here's another way to construct a pointer, unique pointer. I can actually pass in this through the constructor, as we just saw on the previous page, and that gives us something like that there. And then again, I can test that pointer to see if it's managing anything. And if it is, then I can print out what that unique pointer is pointing to, again, overloaded. And then I can reset a pointer, which is different than release. So we haven't gone into release, but reset actually deletes the item on the heap and then nullifies the unique pointer. Or sorry, reset deletes the item on the heap and nullifies the unique pointer. If I were to have used the release method, it would have just released the pointer and not deleted the item on the heap. So that's generally like pulling the ripcord and jumping out of an airplane. You generally wouldn't do that with a unique pointer because you want the unique pointer to manage that heap item for you, okay? So there's our unique pointer. We can print that out, test it, determine whether it's null after. Of course, that would be an error if you try to dereference a unique pointer that's actually null. So, and then here's a couple, just kind of putting it in code, fully in code form here. I won't go through all this, but you can kind of see that stuff kind of holds up. And remember, we can't do, it's a little confusing to remember these two forms of the copy constructor. So if I try to create an instance of anything by passing in an instance of another thing of the same type into its constructor, whether it be a shared pointer or something else, that's calling the copy constructor for this class. But since this class by definition deletes the copy constructor, we would get an error there. And this right here is just another way of doing the same thing, right? So we could pass in a new foo2 into FUP, and that's going to give us an error as well, because that's also trying to copy from an existing instance. And then the assignment between two existing ones is, of course, assignment constructor. So I think you guys have heard that before. We also looked at vectors of pointers, and this you're going to need to do definitely in homework 8 when you convert things over to shared pointers. Not with a unique pointer, but you'll be doing it with a shared pointer. But a vector of unique pointers of type int, right? So that would just be a collection of pointers to maybe your puzzle pieces. But in our case, we would be doing it with shared pointers, right, in homework 8, okay? So that's a very familiar format there. And when we do this, just to point out, that doesn't mean we have any pointers at all. If you recall, vectors are dynamic, of course, and they don't start out life having anything in them. So num pointers is the name of a vector, and it will eventually hold this type in yellow. But until we actually do a pushback of a unique pointer into the vector, that vector is just going to sit there and be empty. But it will know ahead of time that its whole purpose in life is to store unique pointers of type int, right? So that's why we have to specify that up front, okay? So here's some code that we looked at for doing that. I'll just kind of put it all up there. But basically, we kind of allocate the num pointer vector there. And then we prompted the user. We saw this in one of our exercises. And we just pushed back new unique pointers onto that vector every time somebody entered a number. And the really, really nice feature of all this, the key takeaway here is that when I say num pointers dot clear, I'm basically clearing. That's a standard vector method, right? Standard vector method for dumping everything that's in the vector. But as it turns out, since those things are actually smart pointers, their destructors are going to get called and get rid of all these integers that were actually being dynamically created in this inner loop. So you might take it for granted that that cleans things up nicely, but it actually is by virtue of the fact that these unique pointers have a destructor that cleans up what they're managing. So that's a really nice feature. That's this RAII feature that you see out there. So those are the key things we talked about on Thursday. Any questions on that stuff before I kind of dive ahead? Okay. Very good. All right. I realize that's a lot of stuff, and it's a little bit dry, not keeping it in context with a project. I think once you get to your homework 8, and you have already done it all in homework 7, it'll hopefully, and with these exercises we do today, make a lot more sense. So hang in there if you're still feeling a little bit uneasy. So let's take a look at homework 7. This is just chucking one out there for you guys to help you get over the hump on homework 7. So we're looking just at the constructor. So if you remember, for our puzzle, what we want to do is in main, you could create an old school pointer to a puzzle instance, or you could create a shared pointer if you want. But basically, the puzzle instance itself has a couple private members that count the total number of pieces and the maximum row and column in the puzzle, right? And then we have this pointer to a token, right? So it's a token star star, basically. It's called pieces. We have to dynamically allocate this array of old style token pointers. And remember, homework 7 is not about shared pointers. It's all about just the old school pointers. So in homework 7, your constructor, the first thing it's got to do is actually allocate this array, right? But it's the only way it's going to know how many pointers you want is to be able to read the first line of the file. So we'll read the first line of the file, figure out how many pointers we need, allocate those null pointers in here, null token pointers, right? And then we're kind of done, right? Oh, sorry. And then we got to read in the puzzle pieces and allocate each one of them individually, and then point them, set their pointers to be pointing from this array. Again, these are the old style pointers in homework 7. Homework 8 is where we'll convert those to shared pointers, right? So that's what we need to do. So let's take a look at some pseudocode, and hopefully this gives you, 90% of what you need. So our constructor from the puzzle.h file needs starts with a file name. So we have to open that file name, and I'm sure you can remember how to do that. And if you go back and you look at the Canvas description, you'll recall that there's an integer on the first line that's just the number of pieces in the puzzle. So you're going to need to read that in, and that's going to give you the clue to how many of these pointers you're going to need to allocate, okay? So these are pointers to tokens in the piece count array, right? So so what we want to do is after we allocate those, not before, right? Because I've seen people try to stuff pointers into this pieces array before you allocate stuff, and of course your constructor is going to crash. So you allocate it first, and then you go through, and for every row from the file, you're going to read in the letter, the row, and the column number, and create a token from that. And you can create a temporary token instance, or sorry, take that back. You want to create it on the heap here, right? So you're going to use the new command, the new keyword, but you can assign that pointer to a temporary pointer variable inside of your loop if you want. It's entirely up to you. But before you move on to the next token, you have to assign that pointer to a position in the newly allocated pieces array, right? So that's the key part of this, is just getting that stuff done. And then the one little bit here that's going to help you a lot, and also people forget this one too, is you need to monitor for the max row and max column based on the pieces that you read in. Right? You're going to need to know this for later on when you go ahead and initialize your grid to a certain number of dimensions. The only way you're going to know is if you've kept accurate count of the max row and max column. And most people, not most people, I'd say about a third, understandably will get that wrong. They'll be off by one. They'll either have one too many or one too few, and therein lies most of the segmentation faults for homework 7. So if you can get over this part with the constructor, you are well on your way to doing the rest of the assignment, okay? So any questions on that? That's kind of the hint for the day, if you will, on homework 7. That's your puzzle constructor. Everybody good with that? Okay. Very good. Thank you. Okay. So that's just a little review on homework 7. If you need to come back to this hint, it's here for you. It's in the lectures, and of course this lecture will be recorded as well, so you can come back and listen to that again later. Okay. So let's do a couple exercises with shared pointers to make sure that you retain a little bit of this stuff. And we're going to do one of everybody's favorites. We're going to go back to linked lists, but fortunately I've written most of this code for you. But hopefully you remember the idea of a linked list. You have these node class instances that can hold some value. In our case, they're going to be just a character, right? So if I want to print hi there, I want to have all these node instances created, which with these different characters, including a space there in the middle. So that's just a blank basically, but these are all individual instances with a next pointer. Each node has a next pointer that we can link up to the next instance. And so this is kind of our class here. We have a value, we have the next pointer that starts out as null, and a constructor where we put a default in there of the null character \0 in case you forget to send me a value in the constructor. And then I've done this new thing just to help you remember this. If you remember converters, right? Operator char is how we say, oh, I want to convert this node instance to a character. Well, for us, that's really trivial. We just return the val. And what this allows us to do is directly print a node instance. This is another way of allowing the OS stream or the output stream, character stream, to be able to print a node instance directly. It's just a nice thing to have, right? And then we have our destructor that just tells us we're deleting a particular character. Okay, so this is all written for you. This is kind of our base thing. And then what we're going to do is inside of the code, you're going to see we're going to kind of do this very manually. So I've intentionally set this up to cause you to have to do some repetitive learning here. So there is a node for every one of these letters in our message, right? And they've kind of named the variables of the pointers to be something that won't collide. So I have H for the first H and H2 for the second H. So anyway, we have all these things in there. And then we can manually link them together. Of course, we can say H next goes to I next goes to the space, etc. So these things are pretty manual. We could do that in much more elegant ways, but I just kind of laid it out there so it's really simple to see. And then we're going to traverse those nodes, good old classic while loop for a linked list. We set our temp equal to the H, which is coincidentally our head pointer. And then while the temp is not null, we're just going to print out the value of that node, and then we're going to advance to the next node. And we just keep doing that all the way until we get to null. Okay, so that's all written for you. That's our classic kind of linked list. So what I want you to do is go into this REPL and convert that to use shared pointers wherever necessary. And so I'm going to let you kind of see if you can figure that out. There's really not too many places, but basically anywhere you see a node star pointer, you'll want to put in a shared pointer. And pretty much you shouldn't have any or many stars left over. But I'll let you take a look at that and see if you can figure that out based on what we've talked about. And maybe what I'll do is I'll roll back to the slide with the shared pointer syntax on it, so you kind of have a model you can look at while you're doing this. But ask me questions if you have them while we're doing this. Boy, I got to really go back a ways. Sorry about that. Shared pointer, shared pointer, shared pointer. I guess we didn't do that. Well, it's going to be a little bit like this, except it's going to say shared pointer. Sorry, question there. Hold on. Oh boy, thank you for that, Jackson. Yeah, hold on 1 second. 1 second. What I'm going to do is, I totally meant to do that, and I did not. I'll have to play catch up on that. Okay, hold on. Get myself back to where I want to be. Practice. Sorry about that. Okay, I'm going to launch this, which I don't think will pop up in your window, but I'll copy the link, come back to the chat. There we go. So there is the practice. Right. Yeah. So there's practice, and I will get you the solution here in just a second. Actually, let me set a timer on that. While we're going here, let me know if anybody's having any troubles getting access to that. Otherwise, I'll let you guys cook there while I collect a few links so we don't have to do this every time. Thanks again for the reminder. Get that started. There's the corresponding solution for that one. Okay. Ah, blew it. Sorry. All right, maybe I'll wait there before I send you any more to avoid burying you guys in these links. Okay, so one of the things that can simplify this when you think about it is that because of the overloads, anytime you're just referencing an existing pointer after it's already been created or initialized, it's really going to be the same. So there really shouldn't be any changes to your code once you get past the construction phase of it. So the creation of the shared pointer or the pointer or the initialization of the pointer, that's usually where you have to convert the code. Ideally, everything else or most everything else is going to be almost identical, which is great. Okay, well, let's take a look at this one then and see as folks are wrapping up. So here's the node class, right? So so here, rather than our node pointer next, we just say it's a shared pointer of type node, and the name of the instance is going to be next. Now, I know you might be tempted to put star next or node star inside of the template parameters there, but because we're creating an instance of a class, right, that's going to manage the pointer, we don't need to declare it to be a star. It is by virtue of its class already a pointer management thing. It's a class instance here, right? So when we initialize it later on, of course, we'll have to give it we'll have to initialize it the correct way for a shared pointer, but we'll see that in a second. And nothing else in the class actually changes, right? So that's the key part there, right? And so here we go ahead and do the construction of the individual nodes, which you've seen before. We just create a shared pointer this way, right? Okay, so each of these individual nodes are shared pointers, right? And down here, nothing is really going to change up top. You might think that it would, but so we have a shared pointer arrow next. So because we've overloaded the arrow on H, we don't have to change any of this code. It's really nice. We actually just are accessing the next pointer, which points to another shared pointer reference, right? So thus we can use our assignment operator in the shared pointer class to do that assignment, right? And we can do that in the shared pointers, not in the unique pointer. So that's all we're doing here. We're just connecting those things up. No changes to the code here. However, saw a question. 1 second. E2 next. Maybe not. Is there maybe a typo there? So X should be the exclamation point. Oops. It should be defined unless there's a typo that I'm missing or in the code. But hold on, let me see there. Okay, gotcha. All right, no worries. Okay, so right, so that's the only thing we really need to change is temp, right? So if we want to initialize temp to be pointing to something that already exists, we can do that through the shared pointer constructor, right? So we say shared pointer temp, pass in H, or I could say shared pointer temp equals H, and that would also call our copy constructor. Both of those forms would be the copy constructor being called for shared pointer class. And then our code down here doesn't change at all, right? And that's really the goal. Like, so, you have, potentially a very large project you need to convert over. Ideally, there's the code is structured well enough that you just need to convert where it's being constructed and not everywhere else in the code. Okay. So that's that solution. Any questions on that one? Cool. All right. Very good. Okay, so let's take a look at make shared again. So Make shared, as I think I mentioned last time, is a handy tool for ensuring that we, do things as safely as we can. We know how to create a shared pointer like this. We were just doing that a moment ago. But it would be more safe, in fact, if we could create it like this, using this make shared utility. The make shared utility basically says, hey, I'll do the creation around here on the heap. You don't do the creation like you were doing up there. I'll do the creation for you. So give me everything that you were passing to the string constructor, and I'll do the new string construction based on that. So make shared is asking you for the constructor arguments for the template type that you're using. So if this was a foo class, we'd be passing in the arguments for foo, but since it's a string type, we're just passing in the constructor initialization for a string class, which is the string. You can just put it in like that, right? So that's what make shared is doing for us. It's the exact same outcome, but it's safer because we know that no one else has a pointer to what we just created. And the only way, it's sort of sequestered in now in the shared pointer system, the only way anybody can get access to that pointer is by the copy constructor, the assignment constructor, which will make sure that things are done properly. So that's why people use make shared. Basically, it keeps things safe, right? So, so what we're going to do then is, I think this is all stuff I covered. Yep. Okay. So yeah, if you had done something outside of class, outside of the constructor here, and then passed in a pointer, that would be the bad case that you want to avoid. So what we'd like you to do is go into the project you were just working on and essentially eliminate any of the use of the new keyword at any point in your code by switching over to make shared. Okay, and you may have to go back and look at that syntax. I'll roll the screen back so you can kind of see what that looks like. Oops. But go ahead and try to convert that project and figure out what you need to convert and what you can convert. Basically, anything with a new has to go. So give that a try. I'll kind of leave that up on the screen so you can see the comparison. And let me know if you have any questions. I'll give you a minute or two on that one, or about 2 minutes on that one. If it looks intimidating, just remember that make shared is just a kind of like a global function. It comes from the memory library. So you're really just calling a function and you're passing in the constructor arguments for the template type that you're using. So, and it's going to give you back a shared pointer all the time. Maybe another minute or so. So, and there will be a couple questions like this on the next quiz that is out now, and those will of course show up potentially on the final as well. So this kind of syntactic switch from the regular way to the make shared way is important enough. You should play around with it and make sure you're comfortable with it. All right, let's take a look at that code. So basically, we're just converting over all of the construction parts where we set up the initial shared pointer, the original construction, to use the make shared, right? Pretty straightforward. We just have one argument for the node, for our node class constructor, right? And then we apply that, we pass back the shared constructed shared instance to H here, which is also a shared pointer to node. So that all works just fine. Everything else can stay the same, which is really nice, actually. So it's just another way to create that instance of our shared pointer, which is good. Okay. Any questions on those formulations, the make shared or the other project that we looked at? Okay, cool. Great. All right. Well, then let's talk about weak pointers. This is where things get a little bit hard to maybe wrap your mind around in a familiar way, but we'll kind of do it in an abstract way a little bit. So weak pointers are generally made to work with shared pointers. Question. Okay, no worries at all, no worries. I'll just keep an eye out. Sorry, someone was just asking a question on the side. So weak pointers are made to really work in conjunction with shared pointers. So if you recall, shared pointers have a reference count. They keep track of how many shared pointers are managing the same or referring to the same item on the heap. So in this case, we have an integer 5 pointed to by a shared pointer, and it has what's called a use count. Now, if we were to if we just wanted to know, if we wanted to monitor that piece of memory on the heap to know how many things are using it, if we used a shared pointer to do that, we increased the reference count by 1. But we don't really want to participate in the reference count. We just want to monitor what's going on with that particular integer. And so that's what the weak pointer will do for us, right? So if I add another shared pointer, my shared pointer count, use count goes up to 2. And I can check that use count through all 3 of these items. I could check the use count through weak pointer, through shared pointer, or this other shared pointer, and they all should say 2 because there's only 2 shared pointers monitoring that thing, right? And so if you recall, the idea with shared pointers is I delete a shared pointer, it doesn't delete the integer it's referring to until the use count goes to 0. So that's why we don't want weak pointer participating in that use count. We just want to be able to delete a shared pointer, and then when the last shared pointer goes away, it will not only delete what's on the heap there, but it'll also nullify the weak pointer, so letting us know or keeping it valid and keeping us out of trouble, so we don't try to access something that's no longer there, right? So that's what the weak pointer is there for. It's to be kind of a silent partner, you know, participating in the referencing of all these dynamic memory pointers, right? So we use it in conjunction with shared. It's always referring to the same item on the heap as its associated shared pointers, right? So it has to be kind of initialized via a shared pointer. And it also, as we'll see, there's a case where it solves what's called a cyclic dependency problem. That's another key reason for using weak pointers. And in fact, if you start playing around with shared pointers in the optional homework 8, if you were to decide to do the Facebook exercise, you might actually run into this cyclical dependency problem. And the weak pointer is important for helping you avoid that. And we'll do a little project here or practice in just a few minutes so you can kind of see how that problem crops up. Okay. But anyway, when we reset the null pointer, or if the last shared pointer is released or reset, then our weak pointer will go back to 0 as well. So those things are all tied together, which is great. Then we can check the use count at any time. All right. So here's how that code looks. We create a weak pointer. That's a null weak pointer. So its use count is 0. It's not bound to anything yet. We can ask if it's expired, or we could ask what its use count is. If its use count is 0, then it's considered to be expired. So it's I think those two things are the same. I don't think there's really any difference in whether a weak pointer is expired or has use count of 0. Now, a shared pointer, of course, we can create that way. And then we can create another shared pointer, which will up our use count for that particular int on the heap to be 2. And now we can compare those two. They should always be the same because that's just the definition of shared pointers. And if I assign the weak pointer to be equal to the shared pointer SPTR, now it's participating in the count. So we can monitor the count. Still, the count doesn't go up, of course, because weak pointers don't add to the count. And I can check the use through everything if I want. I can check if it's expired, which would be false. But if I reset one of the pointers, the use count now goes down to 1, right? And then if I reset the next pointer, our use count goes to 0. And in fact, that W pointer should have a null marker on it as well. I just didn't add that to the animation, but essentially the W pointer will end up reporting that it is expired in that situation, okay? So that's kind of a typical simple case of applying that weak pointer. So we're gonna have you just do a real simple first exercise. So create a weak pointer, right? Then go ahead and create a shared pointer 1, very similar to what we just saw. I think I changed the variable names here, SP1 and SP2. And then assign the weak pointer to point at SP1. And then print out the use count for the weak pointer, okay? And then go ahead and reset just the SP1 pointer and print out the use count again. Just helpful to see these things in action to kind of convince yourself they're doing what they're supposed to do. So give that a try. And then consider, if you will, which class, seems like a silly question, but you know, what the method use count and reset, where does that method live? In what classes? It is a terribly obvious question, but it's often one that will trip folks up. And I saw some quiz questions this weekend. I thought, a couple people are going to miss this, but I'll come back, circle back to this point and explain why I put that rhetorical question out there. So give that a try. It should just take you a minute or two. I'll set the timer and then we'll look at the code. Thanks. Oh, I didn't give you the link, did I? Did I, or did I? I don't think I did. Sorry, folks. Don't hesitate to knock me on the head if I forget that stuff. Hold on, let me go grab that and send it your way just in case. Much apologies for that. So there's so many things going on my screen. Weak pointer practice. I'll put it in the chat right now. Get my chat set correctly. So there's the practice, and let me get you the solution link. Here's the solution link. I'll get the next two. Right. And our next one is named very similarly, so be careful between this one and the next one. One of them is called weak pointer intro, and the other one's just called weak pointer. So we're on the weak pointer intro pair of links right now. Okay. And while I'm here, I'll go ahead and do the cyclic pointer one as well, which will be coming up. Okay, good. All right, I think I'm back now. I think that should be everything. Okay. Hopefully I didn't break anything in the process. Okay. Bit of a long one. Okay, let's take a look at the code. Pretty easy stuff, pretty much what we just saw. So we have our main, we create the weak pointer, set it equal to, or we create SP1, and then remember, we're creating an SP2, we're passing the SP1 into its constructor. We can also say equals SP1 again. That would be our copy constructor for the shared pointer class. And then here is the assignment operator for the weak pointer class, right? So that's an overload for the weak pointer class that's going to manage the pointer or keep track of the pointer SP1 without increasing its use count, okay? So we can print out the use count. We can reset one of the pointers, which should drop the use count down to 1. Yeah, I think I got that right. To use count for SP1 pointer 1. Oh, right, SP1 should be 0, right? SP2 should still be 1, right? Yep, because we only have SP2 pointing to the memory chunk. And then WP is still 1, right, as well, right, until they go out of scope. And then they would both, of course, get cleaned up and delete the item on the heap, right? So that's a little side point, is when we leave the main function, the fact that SP2 goes out of scope means that the structure will get called, which will delete the memory and which will set the WP count to 0. So if this was inside of a function, that would happen and we could actually test it. But since we're in main here, it's a little bit hidden to us, but that's really what's going on there, okay? Any questions on just that first weak pointer exercise? All right, cool. Very good. Well, I got a good feeling we're going to get out of here early tonight. I know I say that often, but tonight it actually might be true. That would be fun. Okay, so let's talk a little bit about vectors of shared pointers. Again, I think we looked at a similar case like this, but because it's going to be in your homework 8, I just wanted to touch on it again. So here we have our tool class. The idea is we have a tool that we create and then multiple pointers share the tool kind of thing. So our tool has a name. It's just a simple string. And anytime we call the constructor, we print a message that says it was created. And anytime the destructor gets called, we say that that tool is getting deleted. And the idea here is we just kind of want to use a weak pointer to keep track of how many shared pointers are using that same tool. And this is an interesting case because of the way the vector works. I thought it would be good to just kind of go through it. So if I have in my program this inner scope, so I have main, but then inside of main, I have this inner scope in yellow here, right? And I create a vector of shared pointers to tools. I call that users. So these are our users of our tools, right? So that's what this item in yellow here is. That's our users of tools. It's empty, it's a vector, but it's going to hold shared pointers to a tool, right? Or maybe multiple tools. So now if I go ahead and just create on the side here, inside of that scope, a sort of a shared pointer variable that, and then I create an item on the heap, right? So that's totally separate from the vector, right? But if I, and then I point the weak pointer at it so I can kind of keep track of how many people are sharing this tool, or in other words, how many pointers are pointing to this tool instance. Now, if I start pushing these things, copies of this, if I do push back to push that shared pointer back into the vector, that copies the shared pointer. So now I have two things pointing to the tool. I have this outside of the vector one, and I have this pointer instance, shared pointer instance that's in the tool, right? So I'm pushing back basically just copies of that shared pointer, and my use count is going up, right? So it seems kind of strange. I'm putting an instance of a class in the vector. That's really what the shared pointer is. It just so happens that the instance of that class is this special class that manages a pointer to something on the heap. So it can get confusing. You might think, wait, does this need to be tool star? Do I have to have a star somewhere else in here? Is it star users? No, we're just putting instances of the shared pointer into that vector, basically putting a copy of that into there. That doesn't have to be a copy. You could create unique ones, but the point is that what you're putting in is a shared pointer, not a shared pointer to a star tool. It's just a shared pointer of tool, right? And so then we would get that. And that's kind of what we want to look at in our next project, and think about what's going to happen to the use count after this scope goes away, right? So when this scope is done, if WP was created in the global scope or in the main scope, what's going to happen to its use count, right? It's just interesting to see that what we're pointing out in this exercise is the weak pointer can be, miles away from wherever you're creating this data, right? And it doesn't have to be in the same scope at all, which is really pretty impressive, right? You could have the weak pointer pointing to something that was dynamically allocated inside of a function. And it's this kind of strange connection that you get because they're just both monitoring the same piece of memory. It's pretty cool, actually. So let's go ahead and do this. Create a weak pointer that is defined outside of that inner scope. So basically in the main scope, if you will. And then within the inner scope, we want to create this shared pointer that you saw there that manages the saw tool. So just create yourself a saw or whatever kind of tool you want. And then have the WP pointer point to that so it can monitor that specific use of memory, right? It's not monitoring SP, it's monitoring the memory that SP is managing. That's what the weak pointer is doing for us. And then go into your loop and just push back a copy of SP. And if you remember, we've said, for better or worse, whenever we use pushback, it's going to make a copy of that thing right there always. So that instance gets copied. And so even though it's a copy of the shared pointer, what that copy is managing is the same thing. And so the shared pointer class knows, oh, you're calling my copy constructor. Well, I'm not going to let you just copy what's on the heap. I'm going to actually share that pointer because that's what I do. I'm a shared pointer. So even though we're pushing a copy of a shared pointer instance into that vector, we're actually preserving the pointer to that same piece of memory on the heap. So go ahead and do that. And then after the loop, just print out your user count and then reset the original SP and try to print out, monitor through the WP, print out the use count again one more time. And then lastly, outside of the inner scope, once you leave those yellow brackets that I kind of highlighted there, print out the use count one more time for WP. And the key takeaway there is when this inner scope closes down, it's going to do all of that cleanup on that vector automatically, which is pretty cool. And WP will actually end up being able to monitor that even though that local scope is gone, right? And you should see the destructor, the tool destructor being invoked as you leave that inner scope. So give that a try. I think you got the pointer, or the link for that now. Let me know if you have any problems there. Hopefully I got you the right one. You just kind of, whoops, not yet. This guy over here, yeah. Let me set my timer, give you guys a few minutes on that one. I don't think it's a ton of, let me just check the code. I don't think you have a huge amount of stuff to do there, but. Right, yeah, give you a full 3 minutes on that one. There's enough blank space in there that you got to fill in. Also remind you again, there's a difference between resetting a shared pointer or any of these pointers and releasing it. Reset is kind of the proper way to clean things up. Releasing is like pulling the ejection seat button, jumping out of the plane and just, forgetting that you have memory that you have to manage there. Okay, another half a minute. Okay, let's take a look. All right, so I kind of created these colors to help remind us of the scope that we're dealing with here. So that's kind of our main scope, if you will, the cyan. So we create our weak pointer of type tool, and then we enter this local scope here. And everything inside of this local scope, and it could be a function, it could be, some other, section of the code. But basically, anything that happens in here is going to go away when that local scope goes away, right? So, but the interesting thing is that even though, so WP is defined outside of that local scope, right? But I can create this vector of shared pointers that we call users, like tools, tool users. And I create our one standalone shared pointer there that points to a new instance of saw. I did that here with make shared, but you could have done it the other way as well. And then I go ahead and set it, even though this is the really interesting thing, I'm setting WP equal to SP, right? Now WP is out of this local scope. It's defined somewhere else, right? And then I go ahead and push all these copies back in. Now, if this was our smart pointer that we made 2 weeks ago, those copies would probably be shallow copies and we wouldn't have a reference count. But the shared pointer here is actually doing a good job of keeping track of how many pointers are pointing to that same saw that we created up above, right? And we can print out the use count, which should be 5. This says 10, but I think your code might say 5. So it should say 10 if your for loop went to 10, right? Actually, it should say 11 if your for loop went to 10 because we have this extra shared pointer pointing to it as well. So this is 1 plus however many of these copies that we push back, right? Now, if I do an SP reset, it's going to remove 1 from that count, but it's not going to get rid of all that stuff that's pointing to that thing in the user's vector, right? So there's still a bunch of people there using the saw, right? They're all kind of, those pointers are all shoved inside of the user's vector, right? So we can kind of print that out and confirm that. But once that local scope goes away, it's going to blow away the user's vector, which in turn is going to go ahead and clean up the pointers, but it's not going to delete the actual tool until the very last instance of the pointer goes away, right? Which you should see it call the destructor on the tool only one time to tell you that it's deleting that saw. So even though it's going through that array and cleaning up those 10 or 11 pointers, or 5 or 6 in your case with the code, it's not going to delete that thing that's on the heap until it gets to the very last one. That's the point of the shared pointer. And then the weak pointer allows us to just check that after the fact, right? If you were trying to do something like this without the shared pointer, if you needed to know whether something that had come and gone in and out of scope had cleaned up everything that it was doing in memory, you would really have no way of actually monitoring that. So the WP is really powerful in that it lets you do that even from somewhere else completely inside of your program, which is pretty cool. Okay. Questions on that one? Okay, all right. Bear with me. We're kind of coming down to the last one here. I know these things are a little bit abstract. There's just kind of an extra point on that if you need to go back and review these at any time. So last one I want to talk about is cyclic references. And this one I have the risk of losing folks. This is not something I'm going to test you on specifically. I think it's important for you to kind of grok this. And again, if you decide to do the Facebook kind of option on homework 8, rather than just converting your jigsaw puzzle over, then you might need to know about this. It's an interesting one and definitely one that comes up when you look into weak pointers. So here's kind of describe the use case and the problem. So we know that we can kind of track these references with the weak pointer. that's being managed through shared pointers, which is really nice, right? But what we can do is put weak pointers inside of a class instance and then use them in a really interesting way in which they can actually keep count on how many things are referencing them, right? So if you're an instance of a class, you get created and you just kind of, for various reasons, need to know how many times you're being referenced, not how many times you've been instanced. I know we did that with the static members of the class, but this is how many times are you being pointed to, right? So we could actually do that with a weak pointer, right? And then when that pointer count goes to 0, we could conceivably do something in the destructor, right? So here's how that goes. I have a weak pointer pointing to myself, right? So I'm an instance. So this, I set my weak pointer to this, right? So when I construct this, I use the weak pointer. And then if any other instances of this person class wanted to point to me using a shared pointer, I would automatically have a counter that tells me how many people are referring to me, right? So this is a pretty classic problem, is, needing to know, hey, am I still useful in memory? Do I need to be around? So this weak pointer allows us to build that kind of feature into any arbitrary class, which is pretty cool. So it tells me, in this case, you can think of it as the number of friends or people who are referencing me, right? So here's how that code might look. I can set up a weak pointer of the person class called a meref, right? So let's say this is kind of a bit of a strange example. Let's say I have a map of all names of people, right? So Rick, Morty, Jeff, whoever. So those are strings. So that would be the key of my map, and the value would be the instance of the shared pointer, right? So I can look up anybody. Think of Facebook, right? So I can look up anybody by some key, and for the moment, we'll just say that's their first name, right? And that each of those things has a meref, so it can keep track of how many times it's being referenced, right? So that's the meref there, okay? And I can check the use count on that and say, okay, well, I'm referring to myself, sorry, I'm not referring to myself. That's not counted because it's a weak pointer, but the pointer that's in the map of all people counts as 1, right? So now if, let's say, somebody wants to add me to a group, like a Facebook group, or some classification like I'm hungry, it's dinner time, So now I just by virtue of having that reference, that shared pointer be placed in some vector, let's say, vector of shared pointers like we just did, the reference count goes up, right? It goes up to 2. The weak pointer doesn't contribute to that, but I know, oh, I'm part of 2 groups. I'm part of the, I might not know the groups, but I know I'm still belong to some groups out there, and more than one, right? Which is maybe useful information to have. So let's take a look at how that would look. So here's the code for the map. So hopefully you remember, we give a key and then a value. So our key here is the name of the person, and the value is the shared pointer to the instance of that person, and that's our all people map, okay? So that's kind of what we looked at on the other page. And then our vector, for example, if we just want to collect a bunch of people who are in some part of some group, I would declare a vector of type shared person again, call that hungry people. And then to initialize, I do that good old map thing where I say all people Jeff gets make shared person, and then I got to create an instance of Jeff. And note that I'm feeding the make shared parentheses is getting the arguments for the constructor for person, right? Passing a string into the person constructor, and that's initializing that to my shared pointer of something on the heap, okay? So that's just the first step. And if I later wanted to go ahead and say, oh, okay, well, I want to take the all people merefs and I want to point it to myself. So I didn't do it inside of the class constructor here. I'm just doing it manually, right? So I'm pointing it to myself, and it's a weak pointer. So that's all right, right? So that's not a problem. And then I will say, hungry people push back Jeff. Now, the really nice thing about this is that even though it's making a copy, as we were just saying, of the shared pointer, that is the value component of the Jeff key, because of the nature of shared pointers, it's going to go ahead and refer to the same thing on the heap. So now I've bound this shared pointer to this instance in the middle, and I have a nice ref counter on it that's going to keep track of this stuff for me, right? And just because I've hooked this thing up, I don't have to do any more work. As you probably can intuit, the MEREF just climbs and climbs and climbs. The more times I get added to a group, the more my ref counter goes up, okay? So that's a really, really powerful thing, right? So that's kind of one way to do, so that's how you kind of manage to keep track of reference counts with a weak pointer. So that's one use case, which is handy. So let's take a look at the cyclic case, and we'll see if we can do this exercise. It's a little bit tough, but we'll go through it, and that'll be our last one for the day. So there's a very specific problematic case. Actually, let me make sure. I don't know if did I give you guys the cyclic links already? Let me just double check that before I go too far. I lost my chat window. Yeah, good. Okay, you got the cyclic links. Okay, good. All right, sorry. Just wanted to make sure before I go off talking again. Okay, so cyclic case. So consider a shared pointer we use to manage the instance of a person. So we'll use Rick and Morty. I don't know if any Rick and Morty fans out there, but so SP Rick is a shared pointer to a person instance called Rick. And it's going to have a pointer here we'll call best friend, right? BF, best friend. You can only have one of those, let's say, right? So the shared pointer points to the person instance here, and then we'll do a Morty, which is a shared pointer that points to an instance of Morty. And each of those have the potential to be associated with uniquely with one best friend. And let's say that it's a reciprocal relationship, right? So here's how that might go. So we start out life, our best friend reference count is 0, right? And I say, okay, I want to say SP Rick BF equals Morty, right? So now the best friend BF goes from 0 to 2. I think it goes to 2 here because it should have been 1 before. I probably should have had it 1 because we would have hooked up the best friend. Actually, I don't know why that's 2. Sorry about that. I'm a little confused about that. Oh, right. Of course. Right. Because shared pointer counts for 1 reference to Morty, right? And so when we actually throw another shared pointer in there, we are now participating in this other shared pointer, right? So BF for Morty is 2. And then if we hook up Rick to Morty, now that's 2, right? So there are 2 shared pointer instances of each of these. Seems like it's all good, right? So we've got this situation where these 2 things are tracking each other, and we can interrogate and figure out who's best friends with who. The problem occurs when you try to delete them, right? So if Rick goes out of scope before Morty does, we actually reduce the best friend count or use count over here to 1, right? And then if Morty goes out of scope, that goes down to 1, but the memory never gets cleaned up, right? So this is a huge memory leak problem, right? So if you have these cyclical references, and they can be way more complicated than this, in a loop or something, you can definitely get into situations where things just don't go away. You have this memory that's retained, and your program keeps bloating and you don't know why. And it turns out that these things are self-referencing or cyclically referencing, and they don't get cleaned up, right? So it's a bit of a problem. So the thing that we have to do is just introduce a weak pointer for our BF pointer, right? So instead of having BF be a shared pointer, we make it into a weak pointer, right? And so now we're not having any impact. That pointer has no impact on the use count, right? So that use count now just goes up to 1 instead of 2. And then this use count goes to 1. And when we clean up, Rick goes out of scope. This goes to 0. So that can go away. This goes to 0, and that can go away, okay? So it's a little bit involved. It's hard to kind of visualize this, but it is definitely something. If you go down this path to create these kind of friend references or multiple references to something like this between classes, you can run into some nasty problems, and the weak pointer is one path to your solution there. Okay, so let's see if we can do this. So basically, the key thing is that the weak pointer doesn't increase the count, right? And it preserves this ability to do this RAII rather cleanup process. And the only other way we could get around this is to literally go in and unhook the best friend pointers manually before cleanup, which is just kind of a messy way to do the code, okay? So let's give it a try. We'll see how this goes. We want to inspect and run the REPL already that's there. It should run. Note that the person class has a shared pointer to indicate its best friend, okay? And then note that the destructor for Rick and Morty never gets called when the program terminates. This is proof that that cyclical problem exists. We're not seeing a message that indicates that those two classes get destroyed, or those two, because they're on the heap, right? So what you want to do is convert the best friend shared pointer to a weak pointer, right? And then just rerun that and see if you can verify that the message prints out for the destructor, okay? And then we'll give you a couple minutes, and let's just walk through that code together one time before we call it a day, and see if anybody has any questions, okay? So give that a try. I'll put the timer on for a couple minutes, and we'll go through it. Okay, that one should be pretty easy to do. Although it may be confusing, the amount of code change is pretty minor here, right? So we're really just switching over that weak pointer to be, or the shared pointer to be weak pointer, and the magic kind of happens, right? So you may need to sit down and think about this one a little bit just to kind of anchor it in your mind. Like I said, I'm not going to drill you on this. I think there's only some very basic questions about weak pointer on the quiz, and I'm not going to really drive hard on the cyclic thing, but it is interesting. And again, if you do the Facebook version of Homework 8, you might find it helpful. So so that's kind of it. I mean, I'll just put the link again to the Quizlets up there, and that stuff's, there's the breakdown of the individual Quizlets if you're interested in that. Any questions on stuff today, just on the lecture part or the homework that's coming up? Okay, cool. Well, that's a short one. Finally, you get a short one. It's taking a long time. I will let you guys go. I will stay online here. I'll put my headphone on mute, but just kind of ping me in chat, either publicly or privately if you want, if you need to talk about anything, especially homeworks. And otherwise, I will see you on Thursday, and please don't forget about your quiz. I know it's easy to forget. You may want to review the Quizlets before you dive into that, just especially on the smart and weak pointer stuff, okay? Or shared, weak, and unique. All right, well, I'll let you go then. Thanks, everybody, and have a safe week, and I will see you on Thursday.